Hello, everyone. Thank you for joining us today and be welcome to our webinar benchmarking PID controller performance. I'm Vera from Control Station. I work in the marketing department and I will be hosting this webinar with Vince from Control Station and George from Sage Feedback. And before we start, I just want to tell that you are free to input your questions or comments anytime you want. So here in the GoToWebinar control panel, there is a tab named Questions. And in the end of this webinar, George and Vince will be answering these questions. Our presenters today are Vince Heng. He's a DevOps engineer with over 10 years at Control Station. He's responsible for supporting and evolving our suite of products, streamlining development workflows, and interfacing with our service engineers and customers to ensure our teams deliver reliable, easy-to-use software that drives customer success. And George Buckby is the president of Sage Feedback. He's a leader in the process control industry, focusing his career on enhancing plant operations and advancing control systems. For those who are new here to Control Station, we've been driving innovation in process control since the 80s, and we are proud to support customers all around the world, including many of the leading manufacturers across the process industries.
All right. Well, thank you all for attending. The topic for today's agenda would be PID benchmarking, right? So we're going to cover why PID controller performance matters, ways to assess the performance of your PID controllers, as well as introduce a new benchmark that we've developed and had validated with the University of Connecticut, which is OCE, overall controller effectiveness. And then we'll go over some case studies, how OCE is being employed at customer sites. And we'll also be answering questions at the end. So slide, please, Vera. Before we begin, we just want to do a quick survey, just get your feedback, get some, go around the room and just see how PID controller performance is being assessed at your plant or your facility. So we'll give you a couple of minutes or seconds to answer these questions, and then we'll be looking at the results, and we'll go from there. So there's no right or wrong.
This doesn't it, Vince? I mean, it gives us some idea of who's in the audience and what kind of background you have, and then we'll kind of adapt our approach a little bit to what you tell us here in these polling questions.
Great, so I will close the poll and share the results.
Yeah, that looks about normal. So data logs trend. A lot of our customers use PiVision or even old school Excel, right, to track their PID controller performance. A good joke that I see whenever I go on site is the plant runs on Excel or the plant runs on Pi, right? And this kind of just shows you that data logs and trend are the majority of how PID controller performance is being assessed, followed by operator comments, logbooks, and then being able to compare the control loop KPIs if you track them. George, any?
Yeah, good trend here is that we are seeing over time more and more people are actually using some kind of KPIs for control loops to measure performance. And I think, you know, as we go through the webinar today, we'll see more about that. But, you know, if I go back, 10 years ago, this number, compare control loop KPIs, would have been very low, very few people actually doing that. And now that's come up to 23% at least, which is good progress, because it does help to have some kind of standard way to look at control loops and see whether or not they're doing a good job. So that's going to be kind of the focus of today's webinar. So we'll dive into that a bit and see how that might help.
Yeah.
Great. So we'll first start off here a little bit with, so why does it matter? Like, why do we care about PID controller performance? You know, why is it even a topic? Why are we thinking about benchmarking this to begin with? And the reason, of course, is that the controllers control the process, right? They run the process. Everything that consumes energy, everything that produces a result, everything that drives every other metric that your plant management cares about is in some way connected usually to a controller. Maybe it's a PLC with some logic behind it, but for the large part of the process industries, it's PID controls. So whether you're dealing with combustion in furnaces or drying things or mixing and reacting, you know, whatever it is, whatever type of process industry you're in, separations and so on, those operations are always controlled at some level by PID controllers. And therefore the results of those processes are affected directly by the performance of the PID controller. So if you look at the various types of process problems that you may have in your plant or that other plants have had over time, whether it's a quality problem or you're not being able to produce appropriate yield, or they have reliability issues or even safety issues, in large part those can be traced back to some issues with the controls themselves. If I look at some of the biggest safety issues in industrial history, almost all of them have some component of being affected by PID controls malfunctioning at the kind of the lowest level. Usually those big safety problems, big safety incidents, like I take BP Texas City, where 17 people were killed some years ago. Many different contributing factors, of course. It's not just one PID loop goes bad and the whole plant explodes. Many contributing factors, but at the core of that incident, there was a level controller that was left in manual mode. And column overfilled, material found its way to the outside, explosive material, there was a spark, and people were not where they should have been in safe areas, and it led to a disaster, right? A huge disaster. But at the very core of that, the very start of that incident, was a level controller that was supposed to be an automatic that was left in manual mode. So you'll see many of these things related to your overall plant performance can always be affected directly or indirectly by the PID controller that's running a large part of that process.
Yeah, George, so in many ways, the PID controller is the financial heartbeat of the plant. From what you mentioned, right, it's when it's tuned right and it's on, production stays steady, you get very little waste, and then you can either save money or make money or do both.
Right.
But then when it's off,
some people even call it the brains of the plant, right? It's making all those decisions minute to minute, second to second.
Yeah. And so just going back to the idea that this is the regulator of plant economics, you'll see in that circle, each of those topics have something to do with the profitability of the plant, right? Whether it's safety, quality, energy, reliability, maintenance, yield. The PID controller is responsible in some aspects to each of those.
Exactly. And on the next slide, we'll kind of explore some of that a little bit deeper. Like, so what can go wrong with the PID controller that affects all of these parts of the process? Well, certainly, the thing we always think about and talk about first, what kind of jumps to mind is, what about controller tuning? If the controller is tuned too hot or too fast, the process can start oscillating, swinging around, which causes a lack of efficiency, which causes some instability, which can cause quality problems, causes a whole bunch of different things. But there are many other ways that PID controls can fail or fail to do their job. The valve may be sticky, right? And there's no amount of tuning that will fix a sticky valve. So the control valve might be sticky. Or you might have some changes in the process dynamics and the way the process performs that has not been adapted to. We haven't adapted our PID control to the new dynamics in the process. A very common thing, as I mentioned in that last slide, was that loops can be left in manual. You know, if a controller is left in manual, it doesn't matter what kind of valve it has, it doesn't matter what kind of tuning it has, it doesn't matter how it's configured, it's turned off. It's not going to do anything. So how can you expect your plant to operate at its best performance when the controller is left in manual? And we'll see later too that that can also be a sign that maybe something else is wrong in the process. So all the components of the PID controller, the instrument, the valve, the controller itself, its configuration, its tuning, how things are maintained, how it's operated, what mode it's left in, what are the allowable modes, all of those kind of things can have an impact on the performance of the process. And so we have to find a way, when we talk about benchmarking, we have to find a way to how do we deal with all these possible things that could be going wrong with the PID controller so that we can make sure that our plant is operating at its best. So that's what we're going to dive into in this webinar today.
Yeah, and I just want to piggyback on that, George. A lot of the questions we get are, how can I improve my tuning? Are my tuning values correct, right? But we see here that tuning is just one aspect of improving PID performance. There's other factors that can affect it, whether it's process or neglected maintenance. What we like to see is that the instrumentation is actually configured correctly and sending good data to the PID controller before the tuning can even do its job, right? So when people come to us and ask us for tuning help, it's often not just the tuning that needs to be balanced, but all of these other issues as well.
Absolutely, absolutely. Well, let's go on to the next slide here.
Yeah. So we talk about the PID controller being almost the brains of the plant. How can we assess its performance? A lot of what we do when we deploy our monitoring software is we benchmark. So what's benchmarking? I like to do a sports analogy, especially running, because I'm a runner. So when you're benchmarking something, you measure to a certain standard, right? For me, when I'm preparing to run for a 5K, I want to make sure that my run time is around 21 minutes, right? And that's a pretty good benchmark for me. But for people who run all the time, or high-level athletes, right, they're aiming for 16 minutes, 17 minutes 5Ks. Whereas some people who don't run at all, maybe a 30-minute is where they're at. But it just goes to show, right? How do you know where you stand, or where do you want to be when you benchmark? Where do you set your standards, basically? And there can be a variety of ways, right? Whether it's best in company. You have 5 different sites that are very similar. Are you comparing against those other 5 sites, or are you comparing against the whole industry, right? Whether you're in mining, chemicals, food and beverage, or do you want to compare against your own, just other loops within your own plant? So the way you benchmark or assess performance is really going to depend on what the standard is that you set your benchmarking against.
You know, one of the things I often hear, Vince, from people when we first start talking about monitoring and control systems is, well, how do I know that there's even any potential to improve, right? Am I already doing really well, or am I doing really poorly, or how do I even know where I stand? And without some kind of benchmark, something to compare against, you wouldn't even know. So the idea behind benchmarking is, first of all, to understand, do I have an opportunity to improve? And then, you know, kind of select the appropriate benchmark to see, okay, to what level do we want to improve to? Where should we set our targets as well? So this is one of the key concepts in improving anything, really, as Vince said, and I love the analogy about athletics, because you can expand this to any sports that you can think of to look at comparing performance in many different ways. but how do we look at comparing ourselves or the performance of our plant, in this case here, to others? And how do we know where the improvements can be achieved? How do we know where to start? So it's really fundamental to making any kind of improvement to take a look at what are the benchmarks, what do I compare against? And as you said, Vince, if you're first starting out running, maybe you're just comparing against your own personal best. And then maybe as you improve, you're comparing against others in your school or your town. And then eventually, maybe if you're an elite athlete, to comparing against the world. So.
Yeah, and at some point you will plateau, and the improvements will be incremental, right? And at that point, you just want to maintain. There's very little optimization left, right? And now it's just, I can run 20 minutes. Let's keep it at that pace, because the improvements will get smaller and smaller until you get to almost world class or Olympian stats, right? So.
Good. Or at my age, I'd be happy to finish. So. That's good. So let's go on to the next slide here. So when we talk about doing this kind of benchmarking, the question quickly becomes, well, what do I compare against? Do I compare against my own industry? If I'm in the food industry, do I just compare against controllers in the food industry? If I'm in mining, do I compare against mining? Do I compare unit operations? A boiler is a boiler is a boiler. Do I compare boilers to each other? Do I compare flow loops to flow loops? Is there a way to compare level loops to pressure loops? How do I decide what I'm going to compare against? And which kind of metrics should I use to compare? Should I use the metrics that maybe I was taught in the university level, things like integral of absolute error or percent of overshoot on a step change and set point? What are the right metrics to compare, and what are the right groups to compare against? So this idea of benchmarking can quickly get really, really complicated. I can think of probably 60 or 70 metrics you could perform on an individual control loop, and you're certainly not going to want to benchmark 70 metrics across 1,000 control loops to try to see where you stand. We need to do some kind of comparison where we can get an apples to apples comparison, something simple that would allow us to evaluate where we stand at the loop level, and maybe even if we're lucky at the process level or even the plant level, to be able to compare and be able to say, how am I performing against the benchmark? How well are my controllers doing their job? That's ultimately what we want to know when we're talking about benchmarking here, is how well are these controllers doing? How well are these PID controllers doing their job? And that's what we're going to drive for. So we start off with looking at many, many different ways to compare here. And then we're going to, in the next couple of slides, we're going to get down to a specific way where we can do that in maybe a more universal manner, because I'm not going to go to the trouble of trying to compare integral absolute error only for food processing evaporators in the world. I mean, that could be a meaningful comparison, but it's just so narrow that to get us started, it's not what we want. We want something that's going to be a little more broad, a little more universal, that's going to help drive our actions forward. So we're going to get to that in just a couple of slides.
Yeah, and just to drive home that point, the need for apples to apple comparison, right? One of our customers, they know that the flow loop definitely behaves differently from their level loop there. So to compare the absolute error of the flow loop against the absolute error of a level loop, it's not useful at all. And so that need for, I don't care if it's a flow or a level, how can I look at it objectively and know that the controller itself is doing well? That's really what's necessary.
Right. Okay.
Okay. So while we're on the topic of PID controller, just want to do a quick plug for our next webinar. Today's topic is really more broad in general. How do you benchmark good controller performance? But the next webinar will actually go into best practices. It's more technical, teaches you how to consistently tune a PID controller. And so it's going to be led by Chris Egan from Rockwell Automation. It's going to be a really good webinar. Again, it's going to be more technical based, less general, and so it should be a good topic to dive into. So there's a QR code there you can scan. All right, before we get into the topic of the actual metric, just want to do another quick poll so that we can again gauge where the audience is in regards to linking PID performance to plant profitability. So in this case, there is no right or wrong answer, and you do want to check all that applies. It could be all, it could be one or two, it could be none. So we'll give you a few seconds for this before we move on.
And again, we've seen all of these kind of problems happening and challenges with PID performance, and just looking for, in your specific case, which ones do you see at your plant? I really like the last bullet on this one. We don't agree on how to measure PID performance because you have so many, people coming from different backgrounds, and like I said, a lot of times in university level, people are taught to measure things like integral of absolute error or percent overshoot or something like that, which certainly is a measure of controller performance academically, but in the real world, you have things like a loop was left in manual, so it really doesn't matter how much overshoot there is because the loop's not even being used. So, and a lot of debate going on about what are the best ways to measure the performance of PID controllers. So, I'll be curious to see how this plays out in the poll here.
Yeah, I'm going to show the results.
Yes, again, it's 76% of number 3. I've seen that a lot. Yeah, the controls engineer are overtasked, right? A lot of what we're seeing in industry now is you're being asked to do more with less. So fewer staff, but a lot more tasks that you have to handle. And so other issues take priority over control loop performance. And we see that all the time when we're at customer sites. I'm actually, it's funny that the second one is that the plant average is what's focused on next, not the actual dynamics, because again, you wanna generalize rather than look at the individuals of each loop, and so that's also another indicator that there is a need for a way to generalize the performance of a PID controller and of the plant in general when it comes to PID control.
Yeah, quite often I see this as a visibility problem. If people don't know what the performance of their controllers are, how could they possibly make it a priority?
Mm-hmm.
If you don't even have visibility to it, if you're not even looking at it, how would you even know? In the days before we all had lights on our dashboard that told us the air pressure in our tires, people drive around for a year with low pressure in their tires and you'd never know because you didn't have visibility into it. And yet it was costing you gallons and gallons of gas every week because your tires weren't properly inflated. But you would never know, right? You would just never know because you didn't have visibility.
Right.
These days we have monitors on our tires, or many cars do, that tell us when we have low pressure. And so it kind of points us in the direction to say, hey, take care of this and you'll get better fuel efficiency. So in some ways, PID control is like that. The days of low pressure in the tires without being able to see that you had low pressure. It's affecting the performance of the plant. It's costing you money, but you just don't know about it. You don't know about it.
Yeah.
When we start thinking about this, then from how do we get to a universal measure of performance for controllers? We can look around the industry and see if other people have done something similar that has been effective. And indeed, there is a very good comparison for us to use, and that is the metric called overall equipment effectiveness. This was created in the 1960s, related to lean manufacturing and TPM, the maintenance practice. This kind of came out of some work in Japan and then kind of was adapted elsewhere in the world to come up with a universal metric for the performance of a piece of equipment. And it really didn't matter what kind of equipment we're talking about. It could be a boiler, it could be an assembly line, it could be a distillation column, it could be a paper machine, it could be a motor, it could be anything, right? And they came up with this idea of OEE, or overall equipment effectiveness, as a measure of how well is this piece of equipment or part of the process running. And it was made of 3 components. And again, very simple metric here. Availability, that is it running? A number from 0 to 100%, is it running? And then performance, is it running as fast as it should be running? So if it's running 100% of the time, but it's only running at 80% of its rate, then its overall effectiveness is only 80%, right? So that makes sense. And then a third component, while it's running, is it producing good parts without any defects? So is it, it doesn't matter if it's running 100% of the time as fast as it can go, but it's producing only 30% of the parts are good. That's going to be a problem, right? So it's the combination of availability, performance, and quality that drive this metric, OEE. And this became a very good and useful metric for industry to use for a variety of reasons. One is it's quite simple. It's simple to see, simple to understand, simple to measure against. It's kind of universal. It could be applied to anything. Like I said, it could be applied to a bottle filler, or it could be applied to a distillation column or a furnace or whatever. We can compare it, any kind of piece of equipment or process, against these 3 metrics and come up with a universal metric of OEE. Well, that tells us something about that plant. It doesn't necessarily tell us why that problem is occurring, if it has a problem, but it's definitely giving us a number that we can use for comparison and a number that we can use to set priorities. So if I'm a plant manager and I have 5 parallel operating lines, and I have limited numbers of engineering resources, where am I going to apply those engineering resources or capital resources? I'm going to apply them to the line, the production line that has the lowest OEE. We're going to go find out, why is that line running worse than the others? I'll be able to look at that one number and be able to make some useful decisions. And then again, at the lower level, as you dive into that one production line, maybe that's not doing as well as the others, you can look at the individual pieces of equipment within that line and find out why it's going on. So this is kind of the basis for a really good comparison between pieces of equipment. Now, this doesn't necessarily apply directly to control loops, so we're going to dive into that on the coming slides here to see how we might be able to adapt this to something new. So you can go ahead here, Vera.
So going back to what George said about OEE, that's been a metric that's been around 50+ years. And people, academics, have tried to come up with sort of an analog for that in the PID controller world, right? There was the Harris index, and then again, going back to what George talked about, the integral absolute error, and then all of these other metrics that are very useful from an academic standpoint, where there's easy to see numbers from perfectly generated step tests and whatnot. But in the real world, things are not as easy to record or capture. So we looked at the OEE metric and we said, okay, the factors that are being brought into OEE make sense, and can we apply that to the PID controller? In other words, how can we measure the availability of a controller, the quality, the performance, right? We want to capture that, but not to a specific equipment, but to the controls itself. And so at over 35 different sites, collecting 35,000 loop 35,000 different loops. You know, we sort of collated all of this data, and we said, okay, all of these metrics that we're collecting, which one can we use as an analog for these three: availability, quality, and performance? And what we did was we picked about 4 of them, and we worked with the University of Connecticut, and we said, okay, these metrics that we have here, we need a way to correlate them with the performance of the controllers. So which ones make sense? And so we came up with these analogs to OEE, which is for availability. It's whether or not the controller is in its normal mode, typically automatic, right? So if it's not in its normal mode, if it's being overridden, typically by the operator, then the controller is not even available. It's not even being used, right? So that's the availability metric. It's the percent of time the controller is actually operating in its normal or intended mode. And when we look at the quality metric, we want to say, okay, quality, equipment produces defects. How do we make sure that the PID controller doesn't produce defects? Well, in this case, we can say, okay, when you're putting a PID controller into place, you want to maintain certain set point, right? And so that deviation from set point actually gives us sort of a look into how good our quality of control is, right? Whether it's tracking correctly. And so the quality metric, we turn into an analog with the percent of time that the error is, the average absolute error is good. So is it holding set point in that time range? And lastly, we looked at what metric is an analog to performance, right? So if performance is for equipment is that it's running 100% at its max, how can we look at the PID controller to determine that it's operating at its max, right? And in this case, the output, whether or not the output is being constrained, the percentage of time it's being constrained, actually tells us whether or not it can run at 100%, right? So if the output is pegged high or low, or beyond its limits in its saturation region, then we kind of know that it's doing more or less than it can, and that applies to the performance metric. So again, we gathered all of this data from our 35,000 loops at customer sites over 30 different plants, and we gave this data to the University of Connecticut, and we said, hey, look, are these metrics correlated to how well a PID controller performs? And yeah, they said, okay, your metrics make sense. So again, we'll be publishing a paper in conjunction with them regarding our research into how we came up with the OCE number. But these analogs to OEE allows us to determine if the controller is doing job. Is the controller available? Is the controller producing good quality output? And is the controller performing within its intended operating range at max?
Right, and similarly to OEE, this is a nice, simple 3-component way to evaluate the controller that we'll see is pretty universal. So we can go on to the next slide and look at how practical this is as a metric. So we have our 3 components: availability, quality, and performance, and we can evaluate an individual control loop against these 3 components pretty readily and have an answer to that question that Vince was just asking us, which is, is the controller doing its job? If it's left in manual mode, it's not doing its job. If it's oscillating all around and never landing on set point, it's not doing its job. If the valve is always 100% open and there's no control happening, it's not doing its job. So those three components together, we look at a control loop and we say, is it meeting all three of these requirements? And if it is meeting all three of those requirements all the time, then its overall controller effectiveness is 100%. To the extent that it's lower than that, then it's going to have a lower and lower level of performance, and therefore need a higher and higher level of intervention to resolve what's going on. And the great thing about this metric is you don't need to know anything else really about the controller to use OCE. You don't need to know about the scale of the controller. You don't need to know about the speed of response. You don't even need to know whether it's a flow loop or a temperature loop or a level loop, or whether you're in a plant that's making ketchup or a plant that's making oil. I mean, or a refinery making oil and gasoline. It really doesn't matter. We can use this metric universally across all control loops to evaluate how do we stand? How does this controller stand? It's a very good overall high-level metric that can be used universally everywhere. And the other thing that I really like about this metric is that it's simple to understand. And when I say simple to understand, I mean you could explain it to your management pretty easily, right? Management, you're going to waste your breath if you're going to go talk to management about oscillation and overshoot and integral absolute error and settling time and other metrics of control performance. But if you can go and say, here's this one number that tells you whether or not the controllers are doing their job, that's pretty easily received by management, and it's something that can be easily integrated into the way that you set priorities at your plant and get authorization to fix things at your plant by being able to look at this. So we'll dive into that a little more on the next slide here. So we have, with OCE, achieved our apples to apples metric, right? I can say, well, if I have loops that are operating at 0% OCE and loops that are operating at 100% OCE, I know where to work. I need to go work on the ones that have 0% OCE. I don't, doesn't matter, all those other metrics, those 70 or 80 other metrics that you could do on a control loop, doesn't matter. I know for sure if I have a loop with an OCE that's very low, I know that that's a place where I need to work. So I'm easily able to identify those worst performing controllers and use that to help set priorities. But even beyond that, for an individual loop, what's interesting about OCE is we can aggregate it. Like we can take the average OCE for an entire process or even for an entire plant and use that in a meaningful way to benchmark performance. If I go back to the example I gave before, if I have a plant with 5 production lines that are all similar, I could look at the average OCE for each one of those 5 production lines and have some idea where I should put my effort with control engineers, right, and instrument technicians at the plant. I can very quickly identify where should we put resources to help what's going on. It's a very meaningful metric at the loop level, at the equipment level, at the process level, at the plant level, and even at the corporate level if you have similar processes across a corporation. So quite a useful metric. Again, very easily understood, well understood by management and by operations. We now have something, a term we can use to talk to operators about, are the controls doing their jobs well, and we'll be able to kind of pinpoint and find out what's going on there. Anything to add to that, Vince?
Yeah, as we'll see in upcoming case studies, OCE really allows our customers to identify those, quote, low-hanging fruit, right? Because sometimes, as we saw in the survey, controls engineers don't have time to babysit all of the PID control loops, and they really have an intuition about which loops have priority. just by being at the plant and working at the plant and knowing, okay, this loop right here is more important than this other loop right here that may be showing that it's that's oscillating or that it's high, it has high error. But we don't place as much emphasis on it because we know that it's always been that way. We don't have the time to improve it, right? And so as control engineers, you're really balancing your availability, the time you have to work on PID loops and to do all of your other job functions, right? And so OCE really gives you that, okay, these are the low-hanging fruits. Let's compare it against, you know, my assessment of what I know of the plant, and let's go improve things. And so we'll see in these upcoming case studies how OCE is actually being used in industry. So in this case, we have a mining company with three different sites that are very similar. This company specializes in copper, gold, molybdenum extraction and processing. So all of their sites, they have very similar equipment, you know, flotation cells and conveyors, all of that. And so they really wanted to know, okay, how is my site, how is the effectiveness of our PID controllers at this specific site compared to my peer sites, peer facility? Again, we have the exact or very similar equipment. We have very similar control strategies, very similar um, historians. How can we compare a site somewhere in Arizona to, you know, a different site in Utah, etc.? So what they did is over the period of 6 months, they again they captured the OCE data. So this chart here, I just wanted to briefly cover on the left. This is our data set of 35,000 different loops across 30 different sites. Not all the same industry, just different industries. You'll see the ones highlighted are the actual mining company sites that that they wanted to compare to. So these are, again, different locations, but very similar equipment. We're tracking their OCE score. And again, this is just a program that we've just recently rolled out within the last year. So we're adding more and more data to this set. I think we're at somewhere in the order of 50,000 loops now and 45 different sites. But in this case, this company really wanted to know, okay, what is our effectiveness? What is the effectiveness of our control strategies? And you'll see they scored 63%, which is really good actually when you think about the components of OCE being multiplied against each other. You know, you're so used to in school, oh, anything above 70% is average, and then above 80 is pretty good, and then 90 is like excellent. But in this case, we'll see that actually above 40% is really good OCE. The median actually is around 35% OCE. So being in 63% OCE is actually, you're in the top percentile, right? Top 10% of all of the other plants. And so they compared their OCE with the sister sites, which had scores of 37% and 28%. Again, not terrible because 35% is actually industry average from what we've seen in our data set. And 28% can definitely be improved. But knowing their scores in this way, being able to benchmark and compare, okay, our site is actually performing better than the two sister sites at the other location, allows them to prioritize where their controls strategy controls effort can be maximized, right? So a site that's already operating at 62% is pretty good. Let's put some more effort on the ones that are at 37 or 28%. Next slide, please. And so in one of the components of the OCE score is the availability. And when your controller is not operating in its normal mode, it means one of two things. There's either a remote mode being applied to it by the DCS or control system, or most likely the operator has overridden that mode. So the operator has taken control, they manually override it, and they're controlling it by themselves without the PID actually doing anything. So it's really a silent drain coming from these manual override. It's the operator stepping in for quick fixes, and sometimes you want to sort of get into the idea or the rhythm of asking why did they do that, right? Because if there could be a variety of issues, right? A host of issues, whether or not it's the operator trusting the control system to do its job or the PID to do its job, or whether it's allowing the loop to do its job because the control loop to do its job because the instrumentation has the right sensor data coming in, right? Or neglected maintenance, whether or not the hardware has been neglected. Now you have sticky valves and aging sensors and plug lines, and they're sending all the wrong signals down the wire. And so it's the PID is not doing its job, and now the controller has to override it and do it. So
Vince, I always say that a loop-in manual is not the problem. It's a symptom that there's an underlying problem.
yeah, definitely. And so this availability metric in OCE, it sort of drives them to say, okay, why, first of all, why is the loop in manual instead of automatic? And how can we shift this so that the loops, how can we shift the confidence of the operators to operate back in auto? Is it a mechanical issue that we have to fix? Is it a tuning issue? Is it a process issue? Again, diving into this OCE metric allows them to go down into the specific loop. And then in this case, they found that several of their loops have been oscillating and they needed to tune it. And then the second order effect, obviously, is that now that the loop is actually tuned and controlling properly, the operator can now put it back in automatic mode. The availability of the loop increases, and then with increased availability is increased month-to-month OCE tracking. And you can see that's exactly what happened here from between March to July. They steadily improved the loops, each of the loops within a plant, tackling why the loops were not in automatic, and also tackling their oscillation issues with tuning. And then month over month, they steadily improved their OCE score. And then again, having this OCE score allows them to now maintain after they went over those availability issues. So this is just one aspect. Another one is in the chemicals industry. So in this case, there were warning signs that OCE produces before production came down to a halt. Again, we see this is the same scorecard from the same set of data, sorry, that we've seen from earlier. Again, the 35,000 different loops over 30 sites. In this case, a leading national, multinational producer of thermoplastic resins really wanted to know how well they were doing with their control strategies, with their both loop tuning and their monitoring, how well they were running their production. Right. In this case, they were actually the top performer across our 30 different sites in terms of their control strategies and how well they have their control loops and their OCE score in place, right? So their score is 78%, again, which you don't like to see numbers in the 70s or 60s because we're programmed or primed from school to think anything below an 80 is not great. But in this case, 78% is the top OCE score against a fleet of 30 different plants. And having this high OCE score allows them to sort of maintain and optimize where they are and have visibility into the actual low-hanging fruit, the actual loops that that are driving their score down. And we'll see, if you can go to the next slide, in this case, the OCE allows them to not look at all of the different metrics and just focus in on the ones that they can improve so that they can maintain their world-class OCE status among all of their peers across all the different industries. And I'll turn it back to George to sort of talk about, the flood of different KPIs and why OCE stands out as a metric for it.
Thanks, Vince. I think that's it's really important to realize that, yeah, there are these 60, 70, 80, whatever other metrics you can use for control performance. Are they irrelevant? Well, no, not at all. In fact, OCE is a really good metric to drive us toward the loops that need improvement, so we can identify which loops need improvement. And then all these other diagnostics are what help us dive into what is the specific problem. It's almost kind of like going to the doctor, right? You go to the doctor, and you don't go to the doctor on days when you're feeling great. If your OCE is really high, if you're feeling really good, you're able to do all the things you normally do, you don't go to the doctor that day. But when you're feeling poorly, you go to the doctor, and then what do? They take your blood pressure, they take your heart rate, you get blood work done, whatever, you get all these other things done, and then we can diagnose what's actually going on with you. Well, very similarly with all these other metrics of control loops, which are readily available here in Plant ESP, once you know which loops to focus on due to an OCE problem, then you can dive into it and get a specific diagnosis of what exactly is the issue within this loop. And here you see one that has, you've got a lot of different things going on this slide, but you see a lot of green and a little bit of red, and then you can dive right into the red issues and say, okay, and a little bit of yellow and say, okay, wait a minute, looks like we've got an oscillation problem on this controller. Let's dive into that specific issue to see if that might be what's driving this loop to be put in manual all the time. And those kind of things. So very useful, all these other metrics for diagnosis once you know where to look. And OCE kind of tells us where to look, and then all these other metrics help us identify, well, what exactly is wrong. So, and then we can go on to the next slide here. I know we're running close to the end time-wise, and there will be a Q&A session coming up. So if you have questions that you'd like us to address, feel free to start typing them in now in the questions area on your GoToWebinar controls.
Sure,
Yeah, so
you go, Vince.
yeah, I just want to quickly summarize while we're here. The whole topic of today is how do you benchmark PID controller performance, right? We sort of started off with why the PID controller matters, how it's the regulator of plant economics, how it affects profitability, and all these other hosts of issues like safety, and quality. And then we went to how do you assess that performance, right? What is benchmarking? How do you set a standard? What are you comparing against? And then we sort of arrived at the fact that, okay, because we're comparing against different standards, we actually need a universal metric to measure these against that, right? We need something agnostic that applies not just to specific industries or specific loop types or controller types, right? And so we came to this this metric, which is an analog of what's been used for 50 years. And we said, okay, if to look and assess an equipment's efficiency, you only need to look at its availability, performance, and quality. How can we derive that in the PID context, right? And so we looked at the PID controller's performance, availability, and quality, which is this OCE metric, and it gives us a benchmark for objectively comparing and performing our benchmark. And then we look quickly at some case studies. Again, we just started this program, trying to allow all of this data to be collated so that we can again compare more sites against each other. But the way our customers have been using it has been very positive. They're able to go after the low-hanging fruit and go after the easy issues that gets flagged when this metric takes a nosedive. So I'll turn it back to you, Vera.
Perfect. So I will launch the last pool. Is more a contact information for us, and start doing the questions because we received some questions here. So Jordan Vince, for a PID mass flow controller having a gain scheduler where the PV is not achieving the set point, how best can I tune the controller to start meeting the SP?
Well, this really depends on the process, right? So there's no universal answer for this question. It depends on what the process needs and about also what the process can handle. So that would be a really specific kind of case. I think you'd want to have somebody look at it a little more deeply to understand exactly what kind of tuning you should use and so on. Gain scheduling provides, for those who don't know, allows you to choose different gains under different conditions. So that may be, for example, a plant that operates with multiple products. Maybe product A, you use one set of tuning, product B, you use a different set of tuning, or under different conditions of operation. During startup, use one set of tuning. During normal operation, use another. So it's a much more complicated question, pretty hard for us to answer quickly on a webinar, but it would need a little more detail to be able to address. I don't know if you want to add anything to that, Vince.
Yeah, typically, as you mentioned, gain scheduling is for different operating conditions. So in this case, you really have to, we really have to know what the process is and what each of those conditions are, because again, we know that control loops are largely non-linear, and so in different ranges or even again different product feeds, it'll affect what the value should be for you to tune to.
I would say that Plant ESP offers what's called a state-based condition analysis, which allows you to evaluate.
Yeah. So second questions in persistent.
Oh, go ahead, Mira.
Sorry. So in hypochlorite dosing, we see persistent control error from changing flow, variable water quality parameters, and fluctuation NaOCl concentration, forcing operators to run in manual. What control strategy do you recommend when using both flow and residual measurement? And what performance benchmarks should we use to evaluate and compare different control solutions? Very specific.
Again, very process specific and very configuration specific, but definitely you'd want to consider looking at some cascade control strategies there. You also, very much want to look at, is there some way to measure those disturbances that are hitting your process so that you could maybe even in a feed forward way respond to those before you have to kind of wait for the residual to come out of the tank at the end of the process. So if you could measure some of those, some of that variation coming into the process and react to it as it's coming into the process rather than waiting all the way to the end when it's affected your residuals, then you'd have a chance to have a leg up on responding to some of that variability and disturbance. I always like to describe, like, when you're driving your car and you come to a hill, you don't wait until you're halfway up the hill to step on the gas, right? If you see the hills coming, you step on the gas ahead of time. Same thing in a process plant. If you can see a disturbance coming, if you had some way to know that variability was coming to hit you, you could measure that on the incoming flow or the incoming quality of that stream. Then you could respond to it, before it became a bigger problem, before you got halfway up the hill, so to speak.
Yeah. So we received a lot of questions and we obviously don't have time to answer it all here in the webinar, but don't worry that I will get the answers for you all and we will send those from email, okay? I think we have just time for one more. So would these metrics be impacted by a sticky valve and how?
Yeah, of course, a sticky valve usually causes the process to oscillate, right? Because the valve sticks, and then you have the integral action on the controller trying to open it. It doesn't move, and then suddenly it pops to a new position, and then of course it went too far. Now the integral is trying to make it go down and down and down. It doesn't move, it pops down eventually. So this cycle starts, this stiction cycle starts, and so that would affect this quality metric in the, assuming that the cycle is big enough to be meaningful, would affect the quality component of the OCE metric. And so it would point you in the direction to say, hey, something's wrong with this loop. There's this problem with the quality of the loop. And then you can go dive into it and look for those stiction patterns, for example, to see what's going on. So yes, definitely a sticky valve can have a direct impact to OCE.
Thank you very much, George and Vince, for this webinar. I think it was very informative, and for the questions that we've been receiving, I think it was a success. And as I said, every question will be answered and sent by email to you, or maybe our sales representative will call you to start the conversation with you. Okay? Thank you all for attending, and don't miss the next webinar. Mastering PID control, best practice for consistency and efficiency with Chris Egan. Thank you.
Great, thanks, Vera.
All right, thanks everyone. Take care.